Hi, everyone, and welcome to Astro at Home, presented by Discover the Universe. My name is Lindsay Mann, and I'm very excited to present our speaker to you today. Before we get to that, just a few reminders for the chat. Please refrain from spamming, which is sending too many messages at a time so that they end up coming in one after the other. And please be respectful to one another. We also ask that you don't share any personal information just for your own safety. If you break any of those rules, we'll delete your message or possibly put you in a 5-minute timeout, which means you won't be able to ask any questions. And we want questions. Send us as many questions as you'd like about our topic today, which is going to be about the rings and moons of Saturn, sometimes referred to as the Saturnian system, I believe. Our speaker today is coming from Yukon. Christa van Laerhoven is with the University of British Columbia, and she's going to teach you guys all about Saturn. Hey, Christa.
Hello.
I'll hand it over to you.
All right, excellent. Okay, so let's start talking about moons. Let's see, just setting up my Zoom so that I've got it all nice. So Saturn, when you think about Saturn, probably the first thing that you really think about is that it has rings. And I will talk a lot about the rings, but you can't really talk about the rings without also talking about the moons. So let's go ahead and start talking about them. Saturn's largest moon is called Titan. And when the Voyager spacecraft flew by Saturn, which was the first planetary flyby of Saturn, the Voyager spacecraft looked at Titan and went, "It's orange." And that's about as much as they could tell, because Titan has an atmosphere. It's the only moon that has a really appreciable atmosphere, though several other moons have very, very tenuous atmospheres. And this atmosphere was so thick, so opaque, that you can't see through it. If you use cameras that use the colors that our eyes can see, then you can't see the surface of Titan. If you look at Titan edge on, you can additionally see that its atmosphere has a little bit of structure. It's got this this line around the edge, which is a very, very high altitude haze. And this haze, as well as the lower ones, is from something called photochemistry. So what photochemistry means is that it's chemistry, it's chemical reactions, molecules breaking up and recombining, but it's driven by light, by photons from the sun. So what happens is Titan, it has a lot of methane in its atmosphere, and methane is 1 carbon atom and 4 hydrogen atoms kind of around. And the light from the sun comes in, breaks up one or more of the bonds in the methane, and then that broken molecule finds another broken molecule and they combine. So you end up with longer chains of carbon. So you've got carbon, 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 and it's got hydrogens hanging off of each carbon. And so you'll get methane, you'll get ethane, you'll get propane, and higher and higher and higher, longer strings of carbon atoms. And these carbon atoms are the thing that are opaque, that make it so that we can't see through to the surface using light that's visible to our eyes. If you use radar, you can penetrate through the surface. So you have the spacecraft and it flies over Titan, and it sends out a radar wave. That radar wave bounces off of the surface and some of it reflects back to the spacecraft. And if the terrain is rough, then the radar light will scatter all over the place. But if it's smooth, then the radar wave will bounce off nicely and wander off. And you can tell the difference between these two things based on what gets back to your spacecraft. So here, the light toned areas are rough, and the dark areas, the bluish areas, are smooth. So what we're seeing here is the surface of Titan, and it's got a lot of rough, and it's also got these areas that are really, really smooth. And what we think these are lakes, mostly of methane and ethane. Because it turns out that on the surface of Titan, it's the right pressure and the right temperature for methane to be possibly a solid, possibly a liquid, and possibly a gas. Now, this is a kind of an interesting situation, but it's like how water works on Earth. You could have water as snow, and I'm in the Yukon, so there's still snow outside on my yard. You can have water solid as snow or as ice in your drink. You can have water be liquid, like it is in the rivers or the oceans or the lakes. Or you could have water be gaseous. It could be water vapor in the air. That's where we get humidity from. So Titan's got this sort of the same situation that we have with water on Earth. It's got with methane. So these are lakes of methane. One of the really cool things that the Cassini spacecraft also did was it dropped a probe into the atmosphere of Titan. And that probe sent back a whole bunch of photos. And if you look at this photo and you think, gosh, that looks kind of like a river network. If you looked at a satellite photo of the Earth, you could see rivers on Earth doing this same sort of pattern. And so what this is a river. It's just instead of using water as the liquid, Titan has methane. And here actually the bedrock, the rock that this river is carving itself through, is solid water. Role reversal for water. So this is one of the images that the Huygens probe sent back when it was dropped into the Titan atmosphere. One of the things that you can look up on your spare time is that Huygens also had a microphone, and it recorded sounds in Titan's atmosphere as it dropped through. Sound is a wave that needs something like air to travel through. So in space, generally there's no air and thus no sound, but because Titan has an atmosphere, it has air, we could put a microphone on this probe and have it record sound as it dropped through the atmosphere. This is actually the only instance of sound, like actual sound from space, that we've managed to record. There have been other microphones launched on spacecraft, but one of them for the Mars Polar Lander, that spacecraft crashed, so no worky. Another one is the Mars Phoenix lander, and there they didn't turn on the microphone because they thought there might be an electrical issue. So here, this Huygens probe and the microphone that recorded sounds in Titan's air, that is the only microphone that we've flown and had work. So remember here, when we're looking at this picture, what we're looking at is a river network carved by liquid methane. It's like how liquid water works on Earth, but all of the water that Titan has is solid. Titan is really, really, really cold. So all of the water that Titan has is solid, it's ice. And a lot of what we would call the bedrock, a lot of the surface of Titan is made out of water, ice. So solid water is a lot of what makes up the surface here. Once the Huygens probe landed on Titan, we also got another view basically from the surface of this body. And here we can look at the surface and go, God, those rocks, they look kind of roundish. And if you live by a river or by a stream, then you'll notice that the rocks that are tumbled around in the stream or in the river as that water is moving, that knocks all of the sharp edges off of the rock. The same physics is going on here, but with different materials. Here, the rocks are not made of rocks like the stuff on Earth, but it's made out of water ice. And the liquid that's making up these streams and tumbling these rocks around is liquid methane. So that's kind of cool that we've got this situation that works kind of like what we have on Earth, but different material. And by the way, no, do not drink methane. No, that would be a very bad plan. Methane and ethane and so on, they're in the same sort of family as gasoline. So bad plans. Absolutely 100% do not drink that, even if it was liquid. Another thing to note is that for methane to be liquid, it needs to be a lot colder than it is here on Earth. So if you had liquid methane in a cup and you brought it to Earth, it would boil off and become gaseous in very short order. So if you did drink liquid methane, you would A, be poisoned, and B, be very, very cold. So yeah, no, don't do that. Okay. So the last thing I want to like really mention on Titan is that this is the only moon that we've managed to land on besides our own moon. So for the places that we have sent spacecraft and have landed on them, we've got Earth, of course, because we're living here. We've got the moon because we've sent several spacecraft there, and we've sent human astronauts. We've also sent robotic spacecraft to Venus. This was mostly the Russians. And we've sent spacecraft to Mars and landed them on Mars. And Titan is the last member of this group. There is nothing else that we have landed on the surface of. So that's pretty cool and puts Titan in an interesting class. It's a world. It's not a planet because it's not orbiting the sun. It's orbiting Saturn instead. So it's a moon, but it is a world, and it's actually really super interesting. Another moon that I want to highlight for Saturn is called Enceladus. So Enceladus is really cool because down at the bottom, you can see these blue stripes, and it looks kind of like a cat, and I have a cat, so this is a personal experience note. It looks kind of like a cat went, eh, and scratched the bottom of Enceladus, which is, I think, why they're called the tiger stripes. The interesting thing about these tiger stripes located at the South Pole of Enceladus is that there are plumes coming out of these tiger stripes. So here's a really edge-on view of the moon, and you can see these these jets almost emanating from the surface. And all of these jets are associated with these tiger stripes. Like you can trace back the location of these jets, and they land right on these stripes. You can also take temperature data, so you can figure out how much infrared light is coming from the surface of Enceladus. And the places where these stripes are the warmest places on Enceladus. So you get material and warmth emanating from Enceladus. And we think what's going on here is that Enceladus has a subsurface ocean, kind of like Europa. If you watch the last Astro at Home that I did on Jupiter's moons, you can learn more about Europa. But Enceladus too, we think, has a liquid ocean and is venting some of that into space through these plumes. The energy that is required to make something plumy happen is from tides, and tides do two things. First, they will orient the moon so that it always has one face facing the planet. So here I've got if you stamped a smiley face on the North Pole of any moon, then it would always be the bottom of the smiley that was pointed towards the planet. And the other thing that tides does is it will squish your planet, squishy, 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 squishy. And that's because gravity depends on distance. So when you're a little bit closer to the planet, you get stretched out. And when you're farther from the planet, you're a little less stretched. And that squishy squishy is where you can get energy from friction, and you can drive these sorts of energetic plume things. So yeah, so these are the plumes. One of the other cool things about this is that the material here that escapes from Enceladus, it doesn't stay around Enceladus like an atmosphere, because Enceladus doesn't have enough surface gravity to really hold on to a lot of these particles that it's emanating into space. And instead, what the material from these plumes does is it collects around Saturn in a really faint ring. So here is Saturn backlit. So the sun is behind Saturn in this photo, and the spacecraft is looking at backlit Saturn. And you can see all the rings, and they're super pretty. But then the faint ring kind of on the outside, that is called the E ring. And it's part coincidence, part design that the E ring and Enceladus are interlinked. So all of the material from this E ring is stuff from Enceladus's plumes. Another moon of Saturn, which is absolutely fantastically interesting, is called Iapetus. And Iapetus on one side is really dark, really, really, really dark. And on the other side of Iapetus, it's bright, really, 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 really bright, white, reflective. It's completely a dichotomy. It's the two-faced moon. What's going on here, we think, is that we have Iapetus, and that's going around Saturn. And farther out, there's a moon called Phoebe, and Phoebe's really dark, like the really dark stuff on Enceladus. And we think what's going on is that meteors crash into Phoebe, and some of that dust from the impact starts wandering around Saturnian space, and some of that gets collected by Iapetus. It ends up with one side dark, coated with this dark dust, and the other side light, because it's going through this dust in a particular orientation. And this is part of a tides thing, where Iapetus does have one face towards Saturn all the time. So as it's going through, the leading edge gets coated in dust, and the trailing edge doesn't. So Iapetus, if Phoebe wasn't there, Iapetus would be really bright white all over. But because Phoebe is there, and meteorites hit Phoebe and send dust into Saturnian space, some of that dust ends up on Iapetus, and it coats one hemisphere of Iapetus, but not the other. So it's half dark and half light. Okay, so now let's talk a little bit about the rings. The rings are really interesting for a couple of reasons. First is that while Saturn is the only planet that's got really noticeable rings, all of the other giant planets do have rings. Saturn's are the only ones that are really bright. Saturn's rings are probably not terribly long-lived in this bright phase. They would get darker over time as the particles, as the ice particles that make up the rings get dirty. And also from gravitational considerations, the rings will move and spread out and lose material, and are probably not something that would last over the whole age of the solar system. We think actually that Saturn's rings are probably recent-ish, but like recent-ish on solar system scales, not like, you know, your mom remembers a time when Saturn didn't have rings, but like something like hundreds of thousands of years ago, Saturn might not have had rings. So yeah, that's kind of interesting. And the other thing to notice about Saturn's rings is that they've got a lot of structures. There are stripes that are bright, stripes that are dark. The dark stripes are mostly because there isn't material there. And there's a lot of things going on there. So let's try to break this down. Some of the structure from Saturn's rings is from moons. So there are little tiny moons that are orbiting in the same sort of places that the rings are. And they will shepherd the tinier particles in the rings with their gravity. So you'll have, just like a shepherd comes along and it, gently pokes their sheep so that the sheep behave and go where the shepherd wants. These moons poke at the small ring particles with their gravity and will keep them confined. So that's pretty cool. Some of the other things that these moons can do is they can open these gaps. So where the moon's orbit is, there will be no ring particles. And it can also excite waves that are for where the ring particles are just on the edge of this gap. So normally the rings are typically only about 10 meters deep, which isn't very deep. Yeah, only about 10 meters or 30 feet deep. Typically, so if a typical story in a house is a little bit more than 10 feet. So this is like a 2.5-story building high. That's just how thick the rings are typically. But when you have these moons come around, they can excite waves in the particles, in the ring particles, just at these edges. And sometimes these structures can get kilometers high. So here's in particular, a moonlet in the Keeler Gap that you can see these scalloped edges, and that's a gravitational effect from this moon. Some of these moons we've got reasonably good pictures of, and this is a ring moon called Pan, and I really like it because it looks like ravioli, and ravioli is totally one of my favorite foods. What's gone on here is that the original Pan would have been spherical-ish shaped, and then at the equator of Pan gets coated by these ring particles, the ones that it interacts with and could end up sticking. So some of these ring particles end up on Pan's equator, kind of like a tutu, or like a ravioli, depending on if you're into ballet or pasta. And that gives it this ridge around the middle. So yeah, we've got Pan, it's in the rings, it opens a gap, it affects the ring particles at the edge. And some of those ring particles it ends up collecting, and it gives it this ridge that gives it this ravioli shape. Pan is not the only moon in the rings. Some of them are more or less coated with these ring particles. And all of these moons that are in the rings will invoke structure, these gaps or other disturbances right at the edge of these rings. So yeah, that's pretty cool. There are also structures in the rings that are not due to moons that we can necessarily see. So if we think there's a moon there, but we can't see it, it tends to get called a moonlet to indicate it's moon-like but small, moonlet. So this structure that's in this photo, these vertical structures are, we think, from a moonlet. So we can't see the moon, but we can see some of the structure that it drives in the rings. And these vertical structures are kilometers high, and we think driven by a moonlet that's something like a kilometer across. So yeah, there is lots of structure in the rings that's driven by moons. Not all of the structure that's in the rings is driven by moons that are in the rings. Some of the structure of these rings is driven by moons that are farther away. And where you are in the ring, the orbital speed that a ring particle would go there is a harmonic of a moon that is more distant. So if, say, you have a ring particle and it's the amount of time it takes to go around Saturn, its orbital period is half the orbital period for a moon of Saturn, then that can also open a gap. Or if it's a slightly lesser interaction, it can generate a spiral wave. Pardon me. So here on the inner side, the left side, you can see like a bright, dark, bright, dark, bright, dark, bright, dark pattern that's spiraling. And that is a pattern that's driven by a moon, which we can't see here. But yeah, is driven by gravitational interaction with a moon. So that was some real large scale highlights of the moons of Saturn. But let's talk about kind of the overall picture for just a second. In the Jupiter system, we had 4 large moons, and that really makes up the bulk of the Jupiter system. There are some other irregular moons that were captured later, but the moons that formed around Jupiter, it's basically the 4 big ones and a couple of other super tiny moons. Saturn has a lot more moons that are of medium size, and it's only got 1 that's large, and that's Titan. And why there is this difference between the Saturnian system and the Jovian Jupiter system is not understood. Why these systems look so different, what set off causing Jupiter to have 4 large moons, Saturn to only have 1 large moon and several medium ones. We don't know. It's an interesting question. Yeah, it's something that I'm really looking forward to more research, understanding moon formation, which is analogous to planet formation, we think, and how that gives you different sorts of architectures for these different moon systems. A couple of last things to note while I'm on this slide is I've talked about Titan and Enceladus and Iapetus, and like just barely touched on talking about Phoebe, but there are a whole bunch of other really cool moons in the solar system. So for example, Janus and Epimetheus, they switch orbits every once in a while. They are just about at the same distance from Saturn, and they're in a complicated dance where every once in a while they swap orbits. There's also Mimas, which looks like the Death Star. So it's got 1 really, really big crater. So if you've ever seen Star Wars: A New Hope, and they come across this Death Star and they're all like, that's no moon. With Mimas, it's totally a moon. It looks pretty much the same, but it's totally a moon. One of the other really cool ones is Hyperion, which has a very sponge-like appearance. That's not terribly well understood. Probably something to do with it being very low density, but details here, something, we don't know. So yeah, so that is the Saturn system. So if we're thinking about Saturn's rings and moons, some of the highlights are that Titan has an atmosphere, Enceladus has geysers, these plumes that emanate into space. Iapetus is half bright white and half really dark. There are really small moons in the rings, and the rings and the moons interact. So a lot of the structure that is in Saturn's rings are driven by both moons in the rings and moons that are farther away. So that is the Saturnian system, and I would be now delighted to take questions. Okay, I have a list. So let's see. So methane is 1 carbon and 4 hydrogens, and it ends up being a tetrahedron shape, which is kind of like this, with the carbon in the middle and the 4 hydrogens around at the corner. And all of the longer string carbon atoms are because you hit that with a photon of light, and that breaks the bond with one or more of the hydrogen atoms. And then you have a carbon and 3 hydrogens find another carbon and 3 hydrogens, and then they can stick. They can bond where that extra hydrogen would have otherwise been. Let's see. For the number of rings total, that's not a really easy question to answer because there is so much structure in the rings, and it's hard to say what is the beginning of one ring and the end of another. If you've got a gap in the ring, how big of a gap does it need to be before you say, this is one ring and that's another. If it's a super tiny gap, then maybe it's all one anyway. So yeah, I couldn't tell you how many rings there are because that really strongly depends on how you define rings. Let's see. Can a rocky planet have rings? Sure. Yeah, I don't see a problem with that. Yeah, sure. Let's see. Can humans live on Titan without their spacesuits? No. Titan's atmosphere is thick enough, it's dense enough, but it's really, 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 really cold. Also, it doesn't have oxygen in it, so you couldn't breathe. So yeah, no, definitely spacesuit sort of territory. But because it has an atmosphere, you can do other atmospheric things with it that you can't do a lot of other places. So for example, there's a mission called Dragonfly, which wants to fly a quadcopter, like essentially like a super large drone, and land that on Titan and have that fly around Titan and have us learn about Titan and its atmosphere and its surface and all of that. That's super cool. Let's see. Why does Saturn have rings? Oh, that's a good question that I didn't really touch on. We think that Saturn's rings probably came from one or more icy moons. The details here are really tough, and this is still something that's being actively discussed by the community. Probably the latest thinking is that you had a moon that had a whole bunch of ice, and you need that because the Saturnian rings are essentially just made out of ice. And that moon, if it gets close to Saturn, then tides in their extreme can rip something apart. So I showed an image where how if you get close to a planet, you'll get more stretched out. And if you get really close to a planet, then you can stretch out so far that you're not really together anymore. And you can strip the ice off of this moon and have that ice wander around Saturn and become the rings. There are a lot of details we do not understand. This is not this story that I've just told you is a reasonable idea, but we don't know whether or not it's true. There's a lot of things to work out. How many moons of Saturn are livable? Probably, so none on the surface. Enceladus in the ocean, maybe, but it would be like living in the super deep ocean. So that would be, I don't know how livable that is for humans. It is habitable for life generally, probably, but yeah, livable for humans. The gases, where do the gases on the planets come from? So that would have happened in planet formation. So once a giant planet, what will become a giant planet, once you get up to a core that's about 10 times the mass of Earth, then you can start collecting the gas, the hydrogen and helium gas that's around in the planet forming disk. So yeah, you'll hold on to that in the planet formation process. Let's see. Oh, and one of the reasons I'm saying just that Titan is really, 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 really cold is that I think I remember what the temperature is, but I don't remember it with enough confidence to actually quote you a number. But this is something that that you can look up. Yeah. If we landed on Saturn, now that would be interesting. We did once send a probe into Jupiter, and that would be something, you'd get something similar. But Jupiter and Saturn, as well as we think Uranus and Neptune, they don't have solid surfaces. So you fall through atmosphere, and at some point the atmosphere is like just super thick enough so that you die, or have your spacecraft crushed or something, but you never actually hit a solid surface. So that's pretty fun. And I think I'm out of time. Is that correct?
Yeah, we're at the end of our time for today. If you felt like answering any of those questions on social media or anything, you can go for that. We are keeping a list of all the questions we're getting from the kids to help us design some materials in the future. So anyway, thank you very much, Christa, for joining us today and talking about the Saturnian system. I really liked learning about those moons and those tiger stripes. That was pretty cool. And the kids seemed really engaged in the chat today, so that's really awesome. Thanks so much, guys, for participating and asking some great questions. What was I gonna say? It's Friday, which means we're not back tomorrow. And so we'll be back on Monday to bring you guys more astronomy content at 2 o'clock Eastern time, which is Toronto time if you're not in the Eastern time. If you haven't already, give this video a thumbs up if you enjoyed Christa's talk. You can also send some, maybe it's that way, I'm not sure, some emojis in the chat just to tell us how much you liked Christa's presentation today. And if I don't know if I said this already, click the subscribe button and then hit the bell so that you know when we're back again on Monday. Otherwise, we will see you guys after the weekend. So enjoy. Bye.
Bye.